Hi everyone, what I want to do is finish up this chapter by talking about the closed graph theorem, which is it's useful in all areas of math, really all areas of analysis, but it's especially useful when studying Banach spaces of holomorphic functions. And in particular, I've used the closed graph theorem in one of my papers on Toeplitz operators on a Fock-like space. Okay, so what is the closed graph theorem and why is it so useful? And we'll actually, I'll give a very simple but nevertheless interesting example of using the closed graph theorem in the context of the Bergman space of the unit disk. And in the homework, there's going to be a problem on the backwards shift, basically on the Bergman space, and composition operators on the Bergman space. Just very simple using the closed graph theorem. Okay, so let's say we have a linear map, not necessarily bounded, between two normed vector spaces. So okay, so the graph is, well, you probably know what the graph of a function is. Just a set of all x and y in the Cartesian product, and we'll give this Cartesian product kind of the obvious norm in a second. Well, here y equals t of x, right? Okay, so the norm we give on the Cartesian product is just the sum of the norms. So norm of x plus norm of y and big Y. Okay. Yeah, so addition is kind of obvious. I guess I'll just. And scalar multiplication is also pretty obvious. Just add up component-wise, x1 plus x2, y1 plus y2, and yeah, alpha x, y is just y. Yeah, so just a few notes. I won't check this. I won't prove this. Leave this for homework if you so desire. I won't collect it. I'm not really worthy of collecting it. Well, this is a Banach space with this norm, and you can check it's pretty trivially a norm. The zero element, of course, is just 0, 0. Well, it's a Banach space. It's complete if both of these are complete. Okay, so if both of them are Banach spaces, then x times y is a Banach space. And thanks to the linearity of t, you can easily check that the graph of t is a subspace of the Cartesian product vector space. Nothing terribly deep here. So what does the closed graph theorem say? And I'll have to discuss this a little bit more before it might be you might be able to appreciate its power. So the closed graph theorem says, CGT closed graph theorem. If we have a linear map between two Banach spaces, And if it's linear, then t is bounded if and only if the graph of t is closed. So I need to unravel this a bit, kind of what this means. So let me do that right now before I prove the closed graph theorem. This is really a very easy consequence of the inverse function. I think I forget what the book calls it. I think the book calls it the inverse mapping theorem. So what's the meaning of the graph closed? I should say, well, let me write this down. One direction of the closed graph theorem is basically trivial. If t is bounded, then the graph is closed. Okay. Well, if x and y are in the closure of the graph, then there exists xn, t of xn, well, xn, txn are in the graph of t, converging to x, y. So xn converges to x, and txn converges to y. Okay. Well, if x and y is in the graph of t, so if the graph of t is closed, then the closure is the graph. So if the graph of t is closed, then x and y is in also the graph. So this means y equals tx. Right, so the point is xn converges to x, and txn is going to, well, txn is going to converge. It's going to converge, and it's going to converge to tx. Or in other words, let me rephrase this. Maybe I'll make this a little proposition here. It's a little clearer. I think it's worthy of its own proposition. So what we're saying is the graph of t is closed precisely if the following is true. Xn converges to x, and txn converges to y, implies that y equals tx. Now this might look very reminiscent of continuity. Txn converges to tx. The point here is that when we say the graph of t is closed, we're assuming something that is very helpful that is not given to us a priori by continuity, and that is txn converges to something. So to prove that the graph of t is closed, that's the same thing as saying xn convert. If xn, rephrase this. Whenever we have both xn converges to x and txn converges to y, both of them imply y equals tx. So the key here is that all we need to do to show, if we want to show that the graph of t is closed, we need to show that whenever xn converges to x, and whenever txn converges to something, that something is t of x. And when we're proving continuity, we have to prove that txn converges. Here, we're assuming that txn converges. Right. Okay. Right, so I'll maybe make that a little clearer in a moment. So let's first prove the closed graph theorem. And yeah, the proof idea is, it's a pretty common proof idea, is that whenever you assume something is closed, here we're assuming the graph is closed, and whenever that something is a linear space, a vector space, a subspace rather, then you can apply your heavy guns to that closed subspace, which is itself a Banach space, assuming your original space is a Banach space. Okay, right, so let's prove this direction here, that yeah, that bounded implies the graph is closed. Okay. So let's assume the graph of t is closed. So let's assume xn converges to x. So the graph of t is closed is the same thing as saying if xn converges to x, and txn converges to y, then we need to prove that y equals tx. Okay. Well, this is kind of trivial. We don't even need this. We just need to first, by continuity, that tells me, let me make that clear. Okay, just in this direction is not needed. So by continuity, txn, in fact, converges to tx. Well, limits are unique, so y equals tx. So the graph is closed. So let's prove the much less trivial direction that the graph is closed implies continuity. Okay, so yeah, it's a simple but clever idea. So the idea is to look at projection operators on the graph. So let's define P1 from the graph to x, and P2 from the graph to y. Let's say these are just the projection operators onto the first component, so x, tx gets mapped to x, and this gets mapped to tx. Okay. So both of these are pretty trivially bounded on the, So I should say we give the graph of t the norm. Well, it's just the subspace, so it's the same norm as the norm of x times y, the Cartesian product. So yeah, we can pretty trivially prove that P1 and P2 are bounded. Well, this is obviously less than or equal to the norm of x, y. x t of x, and the same thing here. Let's go to the next page. This here, I'll put an x here. Yeah, this is less than or equal to, this equals to the norm of tx. And that's going to be, just over a bit, x times y. Okay, so the point here is, both of these are bounded and are obviously linear. Right. So one thing to notice is that P1 is obviously onto, it's obviously surjective. I mean, it's just, there's nothing to say there. Pick any x and big X, apply x, tx, apply P1 to x, tx, you get x. So P1, this is surjective. And it's also injective. That's pretty, it's not too hard to see. I mean, it's just linearity. So if P1 of x tx is 0, well, that implies tx is 0. So this is 0, t0. Well, linearity says t0 is 0. Okay, so here's the key, and here's the depth of this proof. We're assuming the graph is closed. So the graph is a Banach space. So is this. This is a Banach space too. So I can use the inverse mapping theorem . Right, and I should say why, you might wonder, why do we need y to be a Banach space? We're not using it really here. Well, x times y being a Banach space requires that y and x are both Banach spaces. So so we need x and y to be a Banach space so that any closed subspace of x times y is a Banach space. In particular, the graph of T is a Banach space. And we also need x to be a Banach space to apply the inverse mapping theorem to P1. Right, so let's do that. So by the inverse mapping theorem, P1 inverse takes x to the graph T. Let's see, right like that. All right. And I claim now that P2 composed with P1 inverse is T. Let's check that. Well, obviously, P1 inverse is, well, the element x, Tx in the graph. I mean, that's, sorry, that should be P2. P1 applied to x, Tx gives me x, so P1 inverse of x is x, Tx. Well, P2 just spits out the second, Tx, so so that means P2 composed with P1 inverse is T, and so it's bounded. Because it's a composition of two bounded maps. P2, we basically trivially proved is bounded. And just to remind you, so to use the inverse mapping theorem, we need my linear bijection to go from one Banach space to another. So this is bounded by the inverse mapping theorem. This is bounded. And so, yeah, T is bounded. All right, so let me make clear the point of the closed graph theorem. I didn't make it clear before. Okay, so yeah, so let's assume here, just like in a closed graph theorem, let's say we have a linear map between two Banach spaces. These are two Banach spaces. T is bounded by the closed graph theorem if and only if, or really we just care about the if part. Only if is trivial. It's just T is bounded from x to y if, well, if the graph is closed. And what does that mean? Whenever xn converges to x and Txn converges to Tx, we have, whenever xn converges to x and Tx converges to some y, we don't know what it is, but to some y, we have y equals Tx. Okay. So let's compare that to just a definition of continuity. And you know, as I said before, there is a very important difference. So what's the definition here? Well, we know bounded is equivalent to continuity, so T is bounded. If whenever xn converges to x, we have Txn converges to Tx. Okay? So again, this is really saying two things. It's saying, first and foremost, Txn converges. And it converges to Tx. It doesn't just converge to something, any old little little y and big Y, it's got to be Tx. So by definition, if we want to prove something is continuous, equivalently bounded, we have to prove these two things. We have to prove Txn first and foremost converges, and it just doesn't converge to anything. It converges to precisely Tx. The closed graph theorem allows us to assume that first part. It allows us to assume that from the start, Txn converges. So we don't have to worry about Txn converging. We just have to show that assuming it converges, in fact, to Tx. That's really important for a lot of interesting applications. It really makes proving continuity that much easier. Yeah, let me do an example, particularly what the book calls the two-norm theorem, which I'll immediately apply to the Bergman space. But this alone is a very, very nice application of the closed graph theorem, very typical application of the closed graph theorem. So this is the two-norm theorem in the book. Yeah, and as I mentioned, there'll be an application, two more applications in the homework to the Bergman space. One on proving a composition operator is bounded on the Bergman space, and proving the backwards shift is bounded on the Bergman space. Okay, right. So the theorem says, let's say we have. And this alone is used all the time in probably every single branch of analysis you can think of, operator theory, PDE, whatever. So let's say we have the same vector space X with two different norms. So in other words, we have two norms on the same big X, and they both norms give you a complete normed vector space. Now let's assume there exists M positive where right, where the norm of X and the 1, this first norm is less than or equal to M times the norm, the 2 norm. Okay? Then I claim that there exists K bigger than 0, where the opposite is true. And when this is true, we say these norms are equivalent. They're, for all practical purposes, the same norm. In particular, you have convergence in one norm if and only if convergence in the other. You can check that as an easy homework. Okay, right. So the proof is, well, if you think about it, what do we need to do? We need to prove that the following linear map is bounded. We need to prove that the identity map just takes in little x, spits out little x. Remember, big X is the same vector space, just two different norms on it. So, well, Ix just equals x. It's not a very interesting map. It just takes in x and spits out x, doesn't do anything, just the identity. So. Okay, right, so, yeah, so, yeah, so if so let's say I is bounded. Let's say K is the norm of I, again, well, just from this Banach space to this Banach space. Okay, then what do we have? We have the 2 norm of x is going to be, well, trivially 2 norm of Ix, and we're saying this is bounded. So this is less than or equal to, well, the operator norm, K, times the norm of x in your first space, which is just this here. That's exactly what we need to prove. Okay? So this is our task to prove that I is bounded. And we do that by the closed graph theorem. Okay, so we're going to use closed, yeah, I'm not going to put dots there. Yeah, so let's use the closed graph theorem. Okay, so this really should give you a glimpse as to just how powerful it is to be able to assume this when we are trying to, just to be able to assume this versus just somehow proving that TXN converges. Allowing or being allowed to assume that is just so much easier. So in particular, right, so what do we need to show to prove boundedness? We need to show that whenever xn converges to x and ixn converges to y, we have y equals ix. Let's see what on earth that means. So let's say xn converges to x. Let's be a little careful. This is in the 1 norm. Yes, it's in the 1 norm. I don't want to get my norms mixed up. It's very easy to do that because proof is a bit abstract. Very easy to prove nonsense when doing abstract stuff. Maybe I'll use terminology. Assume this is true. Now in this case, I'll just write it out. Assuming we don't even know what I is, we can assume, because we're trying to prove I is bounded, we can assume Ixn converges to y in this norm here, the 2 norm. Okay. Well, obviously, what is this? This is just, well, it's not x, it's xn. Sorry about that. Okay, so we're allowed to assume xn converges to x and xn converges to y in these 2 different norms. So what I want to do is show that yeah, so we show that y equals, well, what do we have to show? We got to show that y equals ix, which obviously equals x. So we need to show that basically y equals x. Okay. And how do we do that? Well, that's pretty straightforward. Right. So again, this it's unclear. X is Ix. So, okay, right, and not really much to that. You can try the 2 norm first, but that doesn't really work. You can check that yourself. Let's just work with the 1 norm and use the triangle inequality. So we actually haven't used our assumption yet, which is this. So now we're going to use it. So this is going to be y minus xn, xn minus x. Okay, well, this is going to be less than or equal to, what do we have in yellow? We're assuming this is true. So I don't know if this is a good idea to try and squeeze, but I'll try it. Right, so we have xn converges to y in x2, so we want to apply to this one here. It's m y minus xn plus, well, can't do anything about this. Let me not do this. This is silly. Let me move this over a bit. Give myself plenty more room. Sorry about that. So y minus xn, xn minus y. So again, for the first term, we apply what's in the yellow. Instead of x is x minus xn, y minus xn rather. And of course, y, y is in big, everything's in big X. We're not looking at any other actual vector space other than big X. So, so it's m y minus xn plus, oh, sorry, this is 2 norm. Sorry, xn minus y in the 1 norm. Well, xn converges to y in the 2 norm, so this goes to 0. This goes to 0 because xn converges to x in the 1 norm. So by assumption, we have that y is x. Or in other words, y equals ix, which is exactly what we needed to show. So this is the extra part that helped us prove continuity. We're allowed by the closed graph theorem to assume this, and this was just absolutely invaluable. This gave us this bit here, which for free, basically, we get converges to 0. And of course, we have to use this here, otherwise, can't assume. Otherwise, we can't get this goes to 0. But yeah, this is the extra what we're allowed to assume from the closed graph theorem, and allows us to prove this. Okay, so let me do a very quick application of this 2 norm theorem. as I said, I've had to actually do a variant of this in one of my research papers on Toeplitz operators on a Fock-like space. So you definitely do applications of the closed graph theorem or the two norm theorem like this on in research, particularly sometimes just the Bergman space norm is just not a nice norm. You want something different, but you still want it to be an equivalent norm. Okay, so let's do an example. And let's say X is the Bergman space. So here we're assuming P is between 1 and infinity. And just remind you of what this is. All holomorphic functions on a disk where the LP norm on the disk, or rather, right like this. F is an LP of the disk. Okay. So I'm going to make the following claim. Now I'm going to use K because K came from two-norm theorem. There exists K such that the following is true. And the key, let me move this up here. I should exercise better judgment in my board space management, but so I claim there exists K bigger than 0, where the following is true. Just take, well, the LP norm raised to the P of f of z. This is less than or equal to K times, nothing special about these numbers here. This is just an example. So this is less than or equal to, if you just integrate over basically the annulus, inner radius 1/2, outer radius 1 of the same function. And the key here that makes this maybe a little surprising is that this K works independent of my F. Right. So yeah, obviously for any individual F, you can always prove this. It's not a whole lot to prove. But the key here that I'm trying to make is not trivial at all a priori, is that this K works for all F in the Bergman space. All right, and the proof is pretty straightforward. Yeah, so let's say this here, let me save myself some writing. Let's say this here is going to be, designate this as 2 norm raised to the P. And let's say this is just, maybe it's better if I do it this way, maybe it'll be less confusing. I'll just stick the P's. It just looks nicer without P's, but that's okay. Yeah, so the idea is to just define two norms on the Bergman space. So let's say this whole thing here is, let's say this the second norm, and let's say this is my first norm. And this should be a 1 over p. Okay, right. That. Right, so let's say this is one norm, this is another norm. Well, it's really absolutely nothing much to say about that the 2 norm here is less than or equal to the 1 norm here. I mean, they're the same thing. I'm just integrating over something smaller. So obviously, integrate over something smaller. It's smaller than integrating over the whole disk. There's nothing to say really about that. So it takes a little bit of work, but we've basically done the work already. We proved that this is the Bergman space with this 1 norm here is complete. Basically the same proof using the maximum modulus principle. Shows you that the AP Bergman space is complete with this norm. So both of them are Banach spaces. So in a research paper, basically the research paper, if they really like this norm, they would say, by the closed graph theorem, there exists K where this is true. And they probably would not say anything more. They would kind of brush all these details under the rug. But that's why you're taking a course like this, so that you can fill in the details when time comes. And it will come. But anyway, yeah, both of these. They're both Banach spaces. Right, so yeah, we're done. What does the 2 norm say? It says, let's say we have the same x with 2 different norms that make x a Banach space. If the, I have it mixed up, hope I don't. Yeah, I think I do. Let's say, yeah, sorry, I have it mixed up. My apologies. Let's say this is the 1 norm, and let's say this is the 2 norm. So now I have the 1 norm, we're integrating over a smaller set, is less than or equal to the 2 norm. That's really what I want. I mean, it doesn't matter really, but you can always just switch them, but yeah, so these are 2 Banach spaces. M here equals 1. The 1 norm is less than or equal to the 2 norm. And I should say, I think I wrote this. I said this, but I didn't write it down. Here we're assuming this is true for any little x and big X. Anyway, yeah, so two norm theorem, we have both components true. So we're done. we have that 2 norm is less than or equal to k times 1 norm. Or rather, there exists k bigger than 0, where this is true for all f in the Bergman space. Okay. So again, a very interesting statement given to us almost trivially by the closed graph theorem. So very, very powerful result, closed graph theorem. Okay, so I want to finally finish off this chapter with quotient spaces. So maybe what do I want to do? Yeah, let me clear everything and go back. Whatever, I guess I'll should be enough here. Okay, so quotient spaces. And we've kind of discussed a little bit about quotient spaces already, or rather we've done some kind of examples related to the quotient spaces we'll talk about now. Excuse me, needed some water there. Okay, so let's say M be a closed subspace. Let's say X is a normed vector space. Okay, so I'm going to define equivalence relation on X as follows. So both of these we're assuming are in big X. So X is equivalent to Y if X minus Y is in big M, which is the same thing as saying X plus Y equals, or rather, X equals Y plus M for some little m and big M. Okay. So we're going to use standard terminology to denote this class here. Remember what this means. This is, maybe I'll do a Y here. This is just a set of all X and big X. Where X is equivalent to Y. So denote this by Y plus M. M is a subspace, so this has no formal meaning. It's just, it's easy, it's more convenient to write it like this than to write it like this. So we're saying these two are equal. These two by definition, Y plus M by definition is a class generated by Y, where Y is some element in big X. Okay, so, right, so, yeah, a set of all equivalence classes we're going to denote by, well, it's just a quotient. We're just going to take the usual algebraic ring quotient space. So it's just X modding out by M. Right. And this has a vector space structure. It's a little messy. I assume you've done this in advanced linear algebra, but if not, that's okay. So yeah, this is the usual notation for a quotient space modding out by M. I guess you usually do it in a ring with respect to M being an ideal, but anyway. All right, well, 0 is just 0 plus M. Doing not much to that. Addition is kind of the obvious. X1 plus X2 plus M. Scalar multiplication is just what you would expect. I guess I'll use X instead of Y. I don't know, doesn't matter. Well, you could stick an alpha here. Maybe you'd think it's alpha times everything in M, but M is a subspace. So alpha M is just, as a set, it's just alpha. Sorry, it's just M. So, yeah. All right, so just notice that addition is well defined. And we'll explain in a moment why we need a closed subspace. Right, so how do we prove this? Well, right, remember the issue is that we're really adding classes together. And so this addition should not depend on the representative chosen for this class X1 plus M and this class X2 plus M. In other words, let's look at X1, let's say prime equivalent to X1. And let's check, if we do the same thing, X2 equivalent to X2 prime. Let's check that X1 prime plus M plus X2 prime plus M gives me the same class. Okay. Well, remember what this means. This means that X1 is X1 prime plus, let's call it M1. Same thing for X2. X2 is X2 prime plus, let's say, M2. Both of these are obviously in big M. So let's take X1 prime plus M. Yes, let me do it like this here. So this here is going to be X1 prime plus X2 prime plus M1 plus M2. Obviously, this whole thing here is in big M. So they're equivalent to each other. So what does this say? By definition, x1 plus m plus x2 plus m by definition, this is going to be x1 plus x2 plus m. And that's going to be equal to x1 prime plus x2 prime plus. Well, this is just shorthand for the class generated by x1 plus x2 and the class generated by x1 prime plus x2 prime. They're equivalent, so the same class. And this, by definition, again, is x1 prime plus x2 prime. X1 prime plus m. x2 prime plus m. Okay. And this is exactly what we needed to show. To prove well-definedness, that these two are equal. All right, so now let's get out of just pure algebra and talk about a norm. The norm on the quotient space is, it's a little funky looking, I guess. It's hard to, well, it's not really hard to motivate it, as we'll see in a second. It's a norm where, well, it's really kind of the only norm you can really work with, as I'll explain in a second. So it's going to be the inf, not oomph. So it's the infimum. Let's see if I can squeeze this. Of x minus m, or if you wish, x plus m. M is a norm, a subspace, so it doesn't matter. So it's basically, well, the distance between x and big M. That's what this infimum is. It's literally the distance between x and big M. So in that sense, you have x is in big M if and only if the infimum is 0. Well, here we're going to have to assume that x is closed. So I claim that this is a norm. And I'll give you some practice with this. I'll prove this in detail. Right. Yeah, so let's prove that this is a norm on the quotient space. Okay, so first of all, if this here is 0, and this is the norm on x. I don't feel like writing an x here, but anyway. So if this is 0, then by definition of the infimum as the greatest lower bound, there exists, let's say, little mn, where x minus mn is less than or equal to 1 over n. That implies that Mn converges to X, well, this little critter here is in big M. And now we're going to use our assumption that M is closed. Well, if M is closed, X is in the closure. This implies that X is in big M. Otherwise, we don't know. I mean, in general, it won't be. So this is just a zero element, 0 plus M. Remember, that's what the zero element is, 0 plus M. Right. So the norm equals 0 means we're dealing with the zero element. Okay, the triangle inequality is kind of a pain, but I'll still do it. And I'll leave completeness for homework. It's a homework exercise in the book. So wouldn't want to take away all the fun. Okay, so hands getting a little tired. Right, sorry about that. And so as an actual interesting application of the inverse mapping theorem, we're going to prove in a moment basically the first isomorphism theorem for quotient spaces. Or rather, when you have a bounded linear map, we're going to prove the first isomorphism theorem, or a version of that, for Banach spaces. All right, so how does the triangle inequality go? No way I'm going to do this here, so I'll do this in a new line. It's really just like a 511 exercise. So take the norm of x plus y plus m. That's what x plus m plus y plus m is. So this is going to be equal to, maybe make that clear if it's not. So by definition, this is x plus y plus big M. So this is the infimum of the following: set x plus y minus m. So you can do this using epsilon, kind of epsilon infimum definition stuff. I think it's a lot cleaner to do it this way. It's a little tricky, but so let's do something kind of silly. M is a vector space, so these two infimums are trivially equal. Let's say minus m. Yeah, let me write it like this. I'm just including, I mean, this whole thing here is exactly the same thing as this whole thing here. I'm just including another M2. And this is a bit silly because, you know, M1 plus M2 is in big M. Big M is a subspace. So the two sets are trivially equal. But I can use a triangle inequality here, right? And inf is going to preserve You can check that because I'm using a triangle inequality here, it's going to be less than or equal to here. And here the beauty is I'm taking really the infimum of two sets, and that's just going to be the infimum of the first one, or the infimum of the addition of two sets. The infimum of the addition of two sets is just the addition of the infimum, of the infimums. So this is going to be equal to, and yeah, I mean, this is just a triangle inequality here. Well, you just, if you're confused on this, definitely just check that this would be true because of the triangle inequality. So this is going to be equal to the infimum of x minus m1. Or really, maybe just do the definition of infimum, play around with the definition of infimum and check it directly if this is a little confusing. That really shouldn't be, but anyway. And yeah, that's the addition of the two norms. So not a whole lot to the triangle inequality. X all right. I should say completeness is homework, assuming, of course, X is complete. So no reason to think the quotient space is complete if X is not complete. But if it is, then yeah, then it is. If we're dealing with a box space X, then the quotient space is complete. All right, so I want to finish this off by discussing the canonical quotient map and discussing a very standard example of all this where we're taking the quotient space where M is the kernel of a bounded linear map. So and we'll maybe make more clear in a moment, in a little bit, why we're doing all this. What's the main point? Okay, so yeah, let's say we have a norm vector space X and a closed subspace M. So there's always a canonical quotient map, the same canonical quotient map as you do in topology, quotient spaces, or group theory, ring theory, whatever. That's just simply, well, pi x is x plus m. Nothing too mysterious about that. Yeah, so in this case, this is going to be a bounded linear map. You can check that it's linear pretty effortlessly. So let's just look at this norm here in x plus m. Well, this is going to be, by definition, I don't want to write the x plus m here, big X plus m. Well, it's just the infimum of x minus little m for little m in big M. Well, 0 is certainly in big M, so the infimum is less than or equal to x minus 0, and to be clear, this is in big X so this equals the norm of X. So this is certainly bounded. Yeah, it's certainly bounded, and yeah, has operator norm less than or equal to 1. Okay, so let's yeah, put all this to use in looking at a very interesting, important example. Kind of the standard example, you know, in group theory, you know, looking at a quotient group, and that's just the case of, yeah, the kernel of a bounded linear map. Here we want X and Y to be two Banach spaces, and T is bounded linear map between two Banach spaces. And here we're going to let M be the kernel of T, which is closed. The closed subspace, assuming T is bounded, which we are. Okay. So in this case, we have a version of the first isomorphism theorem, which basically is as follows. If the range of T is closed, then there exists a map from the quotient space to the range T where A is linear, bounded, bijective, and A inverse is bounded. Now, basically, by the inverse mapping theorem, you know, if I can prove all this here, then certainly we're done for the A inverse bounded part. Because this quotient space of X is a Banach space is a Banach space. The range of T we're assuming is closed, and hence it's a closed subspace of a Banach space, and hence is a Banach space itself. So that means that, yeah, that means by the inverse mapping theorem, yeah, that means by the inverse mapping theorem, A inverse is going to be bounded. All right, so what's the proof? Well, the proof is fairly standard. You define A in kind of the obvious way, same way you did in algebra. Define A to be, well, for a class X plus the kernel of T, just to be Tx. Okay, so A is well defined, first of all. Well, if X prime is equivalent to X, so what do we mean by well defined? As usual, we need to prove that this does not depend on the representative of this class underlined here in yellow. This definition here is independent of the representative used to define this class. So in other words, if I have X prime is equivalent to X, I need to check that A, X prime plus the kernel of T, which is the same class as AX plus the kernel of T, gives me the same answer. Let's just check that. So if X prime is equivalent to X, X prime equals X plus little m for little m, usually in big M, but big M is the kernel here. Right. Then by definition, x prime plus the kernel of t is going to be tx prime. X prime is x plus m. Use linearity. And use the fact that m is in the kernel, so this is 0. And you get this as tx, which by definition is x plus the kernel of t. Okay. So if we have two of the same, if we have, it doesn't matter which representative of this class I'm circling we pick, we get the same answer. Tx prime is tx. Okay. So it's well defined. Linearity just follows from, let's do this quickly. Really not much to this. So A of alpha x plus m plus beta, let's say y plus m. Well, this is just A of alpha x plus beta y. Yeah, this is pretty trivial. This is going to be t alpha x plus beta y. Linearity. And so this is certainly by definition going to be alpha a x plus m, which is tx, beta y plus m, beta a y plus m, which is just beta ty. Okay, 3. A is bijective. I'll leave the fact that A is bounded for homework. It's a little bit tricky. You need to be a little clever, but it's not too hard. And you just need to be a little clever because, well, you're dealing with the infimum norm. So yeah, I'll not say anything about that. Well, the fact that A is surjective is pretty trivial. So let's say we have tx in range of t. Not a whole hell of a lot to this. A of x plus the kernel t is tx, so that proves A is surjective. Finally, so that proves surjectivity. Injectivity is, easy too. So if A of x plus the kernel t is 0, well, that means x is in the kernel. So then x plus kernel t is a 0 element in a quotient space. So that proves bijectivity. And again, the fact that A is bounded is homework. It's a homework exercise in the book. Actually, all of these are a homework exercise in the book, but I guess the only one is not trivial. I guess the rest are basically trivial. Yeah, so basically we're done. Again, by the inverse mapping theorem, we have that A inverse is bounded. from the range to the quotient space. Yeah, and that really proves it. Not much more to it than that. Okay, so yeah, one last comment. I'll basically write it as a homework. That's also in the book. So something that's quite interesting, if we're in the Hilbert space setting, so if I have a closed subspace of a Hilbert space H, then I claim there exists an isometric linear bijection. Let's call it let's call it A, from the quotient space to the orthogonal complement of M. So in other words, the quotient space and the orthogonal complement are basically the same space. Okay. So we really don't, so basically the punchline here is that, and when we talk about Hilbert spaces, we really don't need the concept, as long as we're dealing with a closed subspace. Oftentimes, sometimes we're not, but if we're dealing with a closed subspace, then we really don't need the concept of a quotient space in the theory of Hilbert spaces. But in the theory of Banach spaces, we simply do not have a notion of an orthogonal complement, in the sense that the orthogonal complement is a subspace of your Banach space. I mean, a lot of people define the orthogonal complement to be a set of all bounded linear functionals that annihilates your closed subspace. Annihilates meaning plug in anything in your closed subspace, you get 0. But that's a subset of the dual space. That's not a subset of your Banach space. So there is absolutely no good concept of a orthogonal complement of a closed subspace that is itself a closed subspace of your original Banach space. The best substitute that we have is the quotient space. Okay? Even that is not, this is not a subspace of your Banach space, but it's just the closest substitute that we have for the orthogonal complement in the setting of a Banach space. Right? And that's, that's basically the point. All right, well, I'll try and go a little quicker when I do compact operators, see how far we get. 2 weeks to go. All right, so long, take care, bye-bye.